Hello and welcome everybody to session 3 of this research seminar on the Port Askaig Formation of the Garvellach Islands and Islay in Western Scotland. My name is David Webster. I'm the meeting secretary of the Geological Society of Glasgow, and the Society is honoured to be hosting this event on behalf of the Cryogenian Subcommission. Here is the summary of the overall programme for the seminar. There are 4 sessions, 2 on the Wednesday and 2 on the Thursday, with a live Q&A at the end of each session. All of the presentations were pre-recorded, so this video was compiled from the respective recordings, and then the live Q&A session at each end was added. So on to the third session, which concentrates on the non-glacial geology. We'll hear first from Ian Fairchild on the dolomite problem, followed by Roger Anderton discussing marine environments, and then Bruce Lavelle discussing continental environments. And these presentations are followed by a short virtual field trip by drone to a remote small island of the group, Garvellachs, with some drone footage shot by Jordan Mertes and narrated by Bruce Lavelle. So on to session 3.
For much of my research career, there has been a problem, the dolomite problem. How is it that such a widely distributed mineral in sedimentary successions, the carbonate that is most supersaturated in modern seawater, is found so rarely in modern environments? And then there is the paleoclimatological paradox, as articulated in Tony Spencer's memoir. In 1971, the prevailing wisdom was that dolomite only formed in hot modern environments. So why is it so abundant in the Port Askaig Formation? In this talk, I will take this multifaceted issue apart and suggest a combination of solutions. Also, I present new data suggesting that dolomite can provide a route into a chemostratigraphy of the Sturtian glaciation. Dolomite is inhibited from precipitating because of specific chemical factors. Magnesium ions in solution need to be dehydrated, and calcium and magnesium segregated into different layers in the crystal lattice. Now, we can overcome this inhibition in several ways. Time. Other things being equal, dolomite formation is enhanced if sedimentation is slow. Some sedimentary dolomite layers reflect slow sedimentation. Subsurface dolomite can also form over long time periods. Secondly, hydrodynamics. Moving fluids replenish the ingredients for dolomite formation. Thirdly, special water. More concentrated fluids supplied more ingredients. Sulfate reduction removes one of the key kinetic barriers. High magnesium to calcium ratio in solution is often the key factor. The photos on the left show an example from the Coorong area of direct precipitation to form what they told me was yogurt dolomite. Well, not an edible dolomite, but a fine textured precipitate as the lake dries out seasonally. And the evidence points to magnesium-calcium ratio being very high in seawater through the Neoproterozoic. In these diagrams of Neoproterozoic carbonate depositional environments, orange denotes dolomite and blue limestone. Peritidal facies are almost always dolomitized, attributable to a high magnesium-calcium ratio in seawater, as in the examples on the right-hand side of the diagram. The same applies in many slow sedimenting, deeper settings where time is ample to allow dolomitization. Shelfal settings are often not dolomitized. Oolitic shoal facies can be either mineralogy. Before the Cambrian, there were no obligate calcifying organisms, so seawater should have had a higher saturation state and carbonates be more widespread even in cool conditions. Nowadays, we do not recognize temperature limits on dolomite formation, but quantitative paleotemperature methods have failed so far, and facies indicators are rather unspecific. Nevertheless, a plausible indicator of warm conditions are ooid shoal deposits because they reflect continuous active evaporation in agitated shallow water. Intriguingly, we find oolitic deposits at several levels in the Losset Formation, but not in the Garvellach Formation, which formed immediately before the Sturtian glaciation. That evidence is consistent with, although doesn't prove, the possibility that the Upper Garvellach Formation reflects cooler conditions as the glaciation is approached. In our studied sections, we find evidence of the former presence of evaporites, now silicified with anhydrite inclusions, at certain stratigraphic levels in different formations. Remembering that some of the most saline evaporated waters in Earth today are in Antarctica, evaporite pseudomorphs in the Scottish succession indicate persistent aridity, but with no temperature connotation. The Port Askaig Formation has undergone green schist facies metamorphism, so it is important to be clear about metamorphic effects when studying the formation's petrology and geochemistry. One informative way of doing this is to look for comparable features in unmetamorphosed equivalents. The thin Sturtian glacial marine deposits in Svalbard that are shown on this slide contain dolomite that compares closely with dolomite in the Port Askaig Formation. Whereas faceting and striations of subglacially transported stones can be seen in the Sturtian of Svalbard, in Scotland, stones cannot be easily extracted from the matrix, and sometimes they show silicious quartz-albite reaction rines forming during deep burial, as in this example on the upper right. In Svalbard, typical dolomite fabrics, centre left, have dolomite crystals around 5 microns, but study of ultra-thin sections, as in the bottom left image, reveals the striking preservation of sub-micron-sized rock flour in shaly diamictites. At their best, dolomite mudstone fabrics in Scotland compare with their unmetamorphosed equivalents, and even somewhat coarser mosaics do not show shifts in carbon isotopes. However, the lower right photograph of a diamictite clearly shows ultrafine crystals will not be preserved, except in replacive silica perhaps. A guideline is that sand-sized and larger detritus is almost always recognizable in the Port Askaig Formation, but silt is often recrystallized. Now to show you two examples where we have made use of carbonate detritus to understand the evolution of the source area for this clastic material. The first example is from the lowest dozen diamictites, D1 to D12. The second is the terrigenous interval above D13, the Great Breccia, mainly corresponding to the interval called the Main Dolomite by Spencer 1971. In diamictites 1 to 12, we see both limestone and dolomite clasts, which differ in colour, as you can see in the photo on the left. In the stratigraphic profile, we see a tendency towards negative carbon isotopes in the middle of the D1 to D12 interval, shown both by limestones and dolomites, and that mirrors the underlying isotope anomaly in the Garvellachs Formation. So it looks as though we are unroofing the lateral equivalence of the underlying formation. In the interval above D13, we start with this unconformity surface I showed you yesterday, which is periglaciated and overlain by a periglacial breccia, a jelly fluctate. In the thin section image in the centre, you can see how angular and ragged are the smaller clasts. Then there is 10 metres or more of dolaranites. Most outcrops look like fine-grained dolomite, but in the photo and in polished samples, you can see the sand-sized fragments of white dolomite. We interpret this interval as fluvial in origin. At the top is a gravelly deposit, represented by a 3-metre thick set of cross strata representing progradation into a body of standing water. The clasts here are both dolomite and sandstone. And here is the corresponding carbon isotope data, 2 of the 3 sections shown being sampled by Alistair Skelton and colleagues. All 3 sections show a central dip in carbon isotope composition, pointing again to an unroofing phenomenon. But the iron poor dolomite clasts differ from dolomites in the Garvellachs Formation. Unsurprisingly, the biggest differences between the sections are in the basal jelly fluctate unit, where the sediment has not been transported far. Here is summarised our data on the detritus. which is admittedly very sparse in the higher parts of the formation. Nevertheless, it is interesting to see a range from 0 to +6 in dolomite class in member 4 diamictites. And these samples will also give us some interesting information on oxygen isotopes, as we will see. Now I will examine the dolomite precipitates, taking you gradually up the Port Askaig Formation, leavened with insights from the Svalbard rocks. Firstly, at the base of the formation, as I explained in my talk yesterday, there is a continuity of the dolomite mudflat sedimentation seen at the top of the Garvellachs Formation into the non-glacial interbed between D1 and D2. Fine-grained dolomite precipitates become reworked into intraclasts and are abraded to small grains. We can contrast this with the distinct ice-rafted horizons shown by the green blobs next to the log. Here is mostly terrigenous sedimentation, as we saw in yesterday's talk, but the photograph on the right shows a distinct pure layer of dolomite precipitate near the base. Within member 1, there is a distinctive interval with lensing dolomite layers in dark blue-grey siltstones and sandstones, as shown in the right-hand photos. This interval was given the name disrupted beds in 1965 by Kilburn et al., who thought that these were boudinage structures. However, when you examine the structure of the dolomite lenses, it is clear that they are early diagenetic concretions, being less compacted than adjacent, less dolomitic sediment, as we can see in the lower centre image. In the disrupted beds, the concretions tend to develop around dolomite breccias, which represent debris flows down a slope from a glacier grounding line. Sturtian diamictites in Svalbard, shown on the left, show morphologically similar concretions. In both cases, the concretionary dolomite is iron-rich, and you can see a contrast with the iron-poor dolomite class in the lower right photo. Such concretions occur in diamictites in Scotland too. Here, the left-hand photograph shows an example of concretion development within a diamictite at the top of member 1 on Islay. The right-hand view shows a lateral transition from partly dolomitized sediments on the far right, with dark grey silicicastic grains still being visible, to purer dolomite on the left. The top of the disrupted beds on Islay is typically composed of pure dolomite, as in this photograph, which represents the end product of this early diagenetic dolomitization process. A similar phenomenon of dolomite replacing shale is found in Svalbard, just beneath the Sturtian deposits. Here is more unpublished information on the Svalbard Sturtian deposits. A log of one locality is shown on the right, with glacial deposits capped by laminated limestones and dolomites. The photographs show rhythmites from around the 30-metre mark on the log. These are lamanites with sediment delivered by ice melt. In the thin section image and the top of the field image, they have been cemented and replaced by furrow and dolomite weathering orange. The rhythmite layers are thinner, that is more compacted, near the bottom of the field image, where they are not dolomitized. Now, the stable isotope data are very informative. The dolomite class, shown by the circles, have both positive and negative carbon isotope values, similar to the underlying carbonates, and reflect the underlying deposits being eroded. The iron-rich precipitates, shown by the triangles, are mostly -4 to -5 in carbon isotope composition. This is the same composition as the cap, and suggests that the synglacial dolomites are just as valid an indicator of seawater carbon isotope values as the cap is. Strikingly, the oxygen isotopes of the dolomite precipitates reach values as high as +9 parts per thousand ppb. Note that any secondary alteration would lower values, not increase them. Given an absence of evaporation, this requires cold marine conditions, noting that a 5 per mil increase in the oxygen isotope value would correspond to a temperature fall of about 20 degrees. So here, geochemistry is giving us crucial information on depositional and temperature, establishing that this type of Sturtian precipitate is indeed glacial-marine. The third level of dolomite precipitates in the Port Askaig Formation is the unit called the Upper Dolomite in Spencer 1971, at the top of Member 1 in the Garvellachs. It is often difficult to read, but an excellent section in Western Akuli starts with a transgressive storm-dominated package above a periglaciated surface. This is a doloaronite composed of reworked piloidal dolomite. Higher in the Upper Dolomite is a bedded unit that can be identified as stromatolitic, with sand-sized sediment being trapped along with dolomite being precipitated. When we see how the carbon isotopes are going, we now see a small shift to slightly negative values at the top of Member 1. In Member 2, there is a shift in sedimentary regime, and Bruce Lavelle has recognised an overall deltaic context of the interbeds, with coarse sediment lobes prograding into often quiet water environments. Dolomite occurs in many thin horizons in Member 2. On the right is a drone image looking down dip above diamictite 30, showing the presence of 6 thin dolomite units separated by coarser sediments. These dolomitic units are all different in detail, but show clear concretionary structure locally, as in the bottom left photograph, dolomitized rhythmites in the thin section photograph above, and dolomite is also reworked into intraclass, as in the upper left thin section photo. So here we come to a crucial issue. Could these dolomite horizons be forming in a freshwater setting? Or do they mark marine incursions, like the famous marine bands in the Carboniferous coal measures? To answer this question, we can turn to our published study on the Maranoan glacial deposits of Svalbard, which formed in an entirely terrestrial setting at a time of very low sea level. They formed in hyper-arid environments like that of the dry valleys of modern Antarctica, as you see in the lower right. Just above the Antarctic image is a cartoon of our overall depositional model, showing grounded ice margins, glacial lakes, streams and floodplains. The cross-plot of carbon and oxygen isotopes is thought to reflect the original depositional conditions. Unmodified glacial meltwater would lead to calcium carbonate precipitates on the upper left of the diagram, with carbon isotope composition controlled by dissolution of detrital carbonates, a mixture of dolomite and limestone. Locally, the metastable cold water polymorph ichhyite formed distinctive crystals, now replaced by calcite. No such pseudomorphs occur in association with the Port Askaig Formation. Now, the key point is that dolomite is only found towards the right of the diagram, from waters that have become evaporated and from which calcium carbonate has already precipitated, increasing the magnesium-calcium ratio of the solution. We see this evaporitic association too in modern hot playa environments. By the way, the Coorong Lake example I showed earlier is in a volcanic catchment with an unusually high magnesium-calcium ratio. So the message is, in the absence of evidence for evaporites, dolomite is a marine mineral. Back in the Port Askaig Formation, Member 3 contains some thick sandstones with evidence of tidal activity, therefore marine. Dolomite occurs as meter-scale bedded horizons in a few locations. The left-hand photo shows that it forms precipitates that displace sand grains and even cause fracturing, indicative of high supersaturation. The precipitates are again reworked into intraclass. We also see dolomitic zones within and at the top of certain Member 3 diamictites. They form uniform fabrics in which detrital grains are suspended in dolomite matrix and are locally reworked into intraclass. The patches of dolomite at the top of D35 are particularly well known because you see them on approaching the landing jetty on Garvellach Island. The top of D35 was an exposed surface with frost-shattered stones, and I therefore interpret the dolomite patches as forming during the subsequent marine transgression. And if we look again at the carbon isotope profile, we see that it has fallen to more negative values. The final dolomite forming level in the Port Askaig Formation is in Member 5, in the middle of a thick succession of quartz cemented sandstones as shown in the log on the left. Dolomite here occurs in a poorly exposed cliff section and well-exposed fallen blocks in association with gravelly sandstones marked as 45 and 46 on the log, interpreted as mass flow deposits. The dolomite is colloidal, and the CL image at the top shows uniform textures in each crystal, indicating it replaced calcium carbonate. The dolomite consists of thin turbidites and is intensively disturbed by syndepositional faults and reworked into the sandstones, sometimes as large rafts. Now we see the whole remarkable picture of a downward carbon isotope trend with time that culminates in the member 5 values, around -5 per mil, that are characteristic of Sturgeon cap carbonates worldwide. The overlying Bunnahabhain Formation also has dolomite that previously some had regarded as the cap, but these deposits are shallow water, and the cap should coincide with a major transgression. So we feel that the member 5 dolomite fits the bill as the true cap. Now, before we confirm that we are indeed dealing with the sedimentary evolution of carbon isotopes, we should take a look at this salutary oxygen isotope data, because it too shows a decline towards the upper parts of the Port Askaig Formation, and the values are too low to be depositional. As you can see by the coding of samples in the diagram on the left, the effects are similar on Islay and in the Garvellachs. We see no evidence of meteoric diagenesis, and so the values must reflect resetting by oxygen isotope exchange during deep burial and metamorphism. But did this resetting affect the carbon isotopes too? An understanding of the metamorphic effects on stable isotopes in carbonates on Islay has been reached by study of veins in relation to sample transects across tectonic zones by my co-author Alistair Skelton and his colleagues in a paper which they published in Journal of Petrology in 2015. This allows us to assess the question as to whether the carbon isotope values of our studied samples have been influenced by metamorphism. The answer is that it's unlikely. Skelton et al. Found evidence for reduction in the delta 13C values as well as delta 18O in certain narrow zones associated with anticlinal cores where there was enhanced fluid flow and associated strong cleavage development. Our cycling regions in the upper part of the Port Askaig Formation are distant from these zones. A second point is that the data trend is the same in the Garvellachs, where there are no tectonic folds or shear zones. Thirdly, dolomite pebbles have high delta 13C values, even when delta 18O is low. The Port Askaig Formation is also low in organic carbon, but there are increasing amounts of silicates upwards in the succession, making it likely that the upwards trend in oxygen isotopes towards more negative values is related to isotope exchange with phyllosilicates. So, in summary, the carbon isotope decreasing trend upwards is interpreted as a genuine marine stratigraphic profile. Now, such a trend has been predicted by modelers studying the concept of a panglacial ocean. And this trend would be a consequence either of low organic productivity or input of volcanic carbon dioxide, or both. Intriguingly, this trend does not start until above the unconformity above diamictite 13, implying that the unconformity is not a snowball Earth unconformity with a deep frozen Earth. In other words, it's different from what we found in Svalbard in the paper by Bennett et al. In 2015. There we had a series of lines of evidence to suggest that there had been a snowball Earth unconformity. But here, the Port Askaig Formation unconformity shows no chemical change across it, and so we do not believe that there is any evidence for a snowball Earth deep freeze. So we are therefore hopeful that people will look for and find evidence of marine dolomite precipitation in other Sturtian successions, as indeed we have found in the thin succession in Svalbard, and that this may be a way in future of subdividing the Sturtian glaciation chemostratigraphically. Thank you.
The interbeds in the upper three members of the Port Askaig Formation are largely clean white sandstones or quartzites, and these seem to be largely of shallow marine or marginal marine origin. And I'm going to talk particularly about the ones in member 3 on Garvellachs, which are particularly well exposed. This is a view from Islay looking northeastwards to the west coast of Garvellachs, and it shows the boundary between members 2 and 3, so we're interested in member 3. The brown rocks here are all diamictites, and you can see between the member 3 diamictites there are 3 interbeds. I'm going to call these for simplicity interbeds 1, 2, 3 and 4. And these are the 4 units I'm now going to quickly run through. On Tony Spencer's stratigraphic profile through the islands, these 4 interbeds are the yellow units at the top. So I'm talking about them where they're exposed on Garvellachs, which is the island on the left. You can see the lower yellow unit is the thickest, and it's got an erosive base. It seems to cut through the stratigraphy. The next 2 are fairly sheet-like, and then the 4th one is just a little sort of pimple on the top of this section. This is where they're exposed on the map of Garvellachs. Note that the island's been twisted round, so north is pointing bottom left. So what I'm going to do first of all is to look at interbed 1, which is exposed here on the east coast and also here on the west coast. So this is on the east coast, so you're looking southwest, so the bed's dipping to the left. On your right we have the member 2 rocks, and then on the left we have the base of the D33 diamictite, and the interbed, this interbed 1, is this low ground in the middle of the bay. It may be surprising that these quartzitic sandstones occupy the low ground compared with the diamictites, but because they're heavily jointed, they're actually more prone to erosion than the diamictites are. If you go to the bottom of the sequence, you can see this decimeter thick bedding of white quartzite, a lot of jointing, rather difficult to see what's going on. If we go up a little bit, then we can see the bedding, and you look carefully and you realise that the bedding is going in different directions at different places. You can divide the succession up into packages with truncations between these various units, shown here, for example, C, D and E. And clearly what we're looking at, we can measure the orientations. These packages are all cross-bedding. So packages are cross-bedding, dipping at different directions. If we a bit further, we saw C, D and E in close-up, and that's the whole succession. And you can see packages A up to G are cross-bedded. They have different orientations with the boundaries marked.
Once you get to unit H and above to the left of the picture, everything starts to be fairly parallel and normally bedded, but the lower part of the succession is made of thick packages of cross bedding. This is showing them on the log, and you can see they're immensely thick. They're up to 7 or 8 meters thick. Paleocurrents are indicated by the arrows, and you can immediately see that the directions are variable, and they're actually bipolar in places. The flow seems to be going in opposite directions in adjacent beds. The very top succession from H upwards, there isn't much shown, and that's because these units at the top are very highly reworked. It's very difficult to see any structures in, and they're sort of parallel sided, whereas the units below have what were originally muddy drapes along the foresets, so you can see the structures. So there's a significant difference between the top and bottom of the section. And a slight enlargement here of part of the succession, you can see very readily that the current directions are going in different directions and in opposite directions in places. So, you're immediately drawn to the idea that these are tidal sand bodies of some kind. Here's a view on the west coast. You can see 2 packages here, and the cross bedding is shown up because of these thin muddy drapes along the foresets, dividing them into sort of decimeter thick packages. But when you look in detail, they're quite complex internally. Now this unit, as we saw on the stratigraphic profile, has an erosional base. It's very thick, 50, 100 meters thick. It's got these mega foresets, and these indicate, because the foresets are sort of getting on for 7 or 8 meters thick, water depths of at least 10 meters and maybe several tens of meters, and some kind of confined flow, like a channel of some kind. The upper part of the section, there's no evidence of that confined flow, and it may be that the environment was less topographically constrained and it accumulated more slowly with more reworking. So the kind of environment that one envisages for this is some kind of tidal estuary or tidal channel, and as we think there is erosion at the bottom, we can imagine this as being a severely eroded surface at the top of member 2, forming valleys, and then a transgression has worked its way up the valleys, and these big cross beds are deposited in big bed forms in a sort of tidal channel as the valley fills up. As the area gets drowned, the topography might get more subdued and the bedding more horizontal, if you like. So it could be that M2, M3 boundary records a period of subaerial erosion and low sea level. At the top of the unit, the next diamictite D33 advances across the top of the interbed, but you can't really make much in the way of conclusion of what was happening there because it's an erosional surface. Did the ice rather just advance into the shallow marine environment, or had sea level fallen, exposing these rocks? You can't really tell. Let's move up to the next one now, the interbed 2. That's exposed in the on the east coast, but in a little bay called Bothy Bay, and also on the west coast. These 2 sections are about 800 meters apart. So in Bothy Bay, we can see on your right the top of D35, and on your left the base of D36, and again this interbed occupies low ground, a bay in between. On this close-up, the base of D36, nice, absolutely dead sharp boundary with sandstone underneath, and you look to the right, you can divide the quartzites into packages with truncations between them. Again, we're looking at packages of cross-bedded sandstone on kind of meter scale. If we look down dip at the section, we can divide it into a whole series of packages with cross-bedding going in different directions, as you can see. Tony Spencer's found some diamictite in the middle of this section, so it could be that ice was present nearby and we've got ice rafted debris in association with these crossbeds. Now, the other thing to note that at the bottom of this section there's an exposure gap, which usually implies there's some soft rock that's no longer there, has been eroded away. When we look at this section on the left here at Bothy Bay and the equivalent one on the west coast, they're very similar. They both have this exposure gap at the bottom with cross-bedded sandstones above. You can see the paleocurrent directions, again, various directions, a little bit more going in one direction than interbed one, but variable. And I want to draw your attention to the very bottom of the section in Bothy Bay. Here we've got a very nice example of sandstone polygons, sandstone wedges, with a little winnowed lag at the top. So looking at this in detail, we see the sandstone wedges, a pebble lag on top indicating that the top of the diamictite D35 has been winnowed, the fine sediment has been washed away until an armoured pavement of gravel has been left behind. And then the interesting thing is that on top of this there isn't coarse cross-bedded sandstone but silt, very fine grained sediment, and then some little cross-laminated packages of silt which pass upwards into sand. So in other words, this D35 surface looks as if it's suffered what you might call a low energy transgression. The sea level's risen across the subaerial surface, the top of the diamictite has been winnowed, fine stuff has been washed away, but it's essentially a low energy situation. And it's only as the sea level gets, as the sea gets deeper, that we get a high energy environment where the cross-bedded sands accumulate. Let's go over to the other outcrop on the west coast. Same section, we see the dip slope, the D35 dip slope on your left with the sandstone polygons on it, and D36 on top of the cliff on the right, and all the stuff in the middle is the interbed 2. So looking at the circled area in more detail, you can see very nice planar cross-bedding at the bottom, fairly steeply dipping to the right, and it's overlain by a more gently dipping package of cross-bedded units. And the boundary between the two is interesting. It's quite irregular. It's not flat. It's almost scoured. One wonders whether this is some kind of subaerial erosion surface. Could the lower units be a kind of bank margin deposit, and then what we see above that red line are sort of bank top deposits in a tidal channel or estuarine channel, tidal inlet, something like that. When we go to the upper part of the section, there are these really mega faucets. Again, we're talking about 7-8 metre kind of scale. Huge, great, thick mega faucets. And looking at a rough sketch of the orientation of these taken from the hillside opposite, they have a slightly sigmoidal shape, and they also vary in steepness. So you go from fairly steep to slightly flatter, and then steeper, and then flatter crossbeds. This looks like the kind of sequence where you get packages which are separated by what are sometimes called reactivation surfaces, where the slope has moved forward by accreted forward from left to right, and then it's got slightly eroded back and slightly flattened off by either opposing currents or a different current regime, and then the bank or the bar margin or whatever it is then advanced a little bit and then got eroded back, and then advanced and got eroded back. Again, this is the kind of thing that you associate with tidal conditions, with tidal channels, where we get an alternation of faster and slower current conditions reflecting tidal cycles and the like, enhanced by storms and whatever. So looking at the two sections again, you can see at the top right hand we've got these really thick mega faucets, but they don't exist in Bothy Bay 800 metres away on the left. It's almost as if we've got a sort of bank margin situation on the right, whereas a bank top margin on the left. So quite a complex paleogeography going on here. Looking in detail, you can see different densities, if you like, of lamination in this cross-bedded package. You can see some packages with very fine scale lamination produced by little clay, what would originally have been clay drapes, and other packages that look quite clean. This is a bit tricky because it depends quite a bit on how the rocks have weathered out, but it is kind of consistent with the kind of tidal environment where you get an alternation of high energy and low energy tidal cycles. So you get clean packages and then you get slightly more muddy packages when the currents are a bit slower. And you also get this kind of thing, which is rather nice. On the foresets in the area indicated here, you can see that the laminae are not accreting parallel, but they're accreting up the slope. In other words, the sediments are moving, are building up, or probably more likely highly obliquely to the slope, as if the flow is going up the slope or obliquely up the slope rather than down the slope. Again, good indication of kind of tidal environment. So what can we say about this interbed? Well, it's thinner than interbed 1. It's also got a very sheet-like geometry. No evidence at all of erosion at the base, quite the reverse. We've got mega foresets, so again a sort of confined tidal system within some kind of channel. But we have the sandstone polygons at the top of D35 overlain by a poorly sorted winnow gravel and then fine sediment, indicating a low energy transgression. This is possibly a sort of upper estuary, tidal, flat lagoon, whatever you want to call it, environment, shallow water environment. And then as the water has got deeper, as the sea level has risen, it's got deep enough for the large tidal bed forms we see in the upper part of the package to be developed. And we've also seen in comparing the two logs from two areas that we have a difference from, say, a channel access or a bank margin situation on the west coast to a flatter bedding of the bank top in Bothy Bay. So again, complex environment, complex paleogeography we're looking at here. Moving on again, interbeds 3 and 4 shown here. Again, similar place to the previous one. Interbed 4, there's just one section right on the tip of the island. So this is the west coast, interbed 3. At the left, we've got D36, another diamictite. And you can see where I've indicated the dolomitic sandstone, the rusty colour, and you trace it along and it disappears because it's cut out by the first package, which is outlined with the black lines, which you can see cutting down. So this lower package is quite strongly erosional. It cuts down through the underlying units and it's quite massive looking. It looks like an event bed. In other words, something where you've got powerful erosion that's cut down through 1.5 meters of sediment, and then immediately you've got a very rapid dump of sand without much in the way of internal structure, so without much in the way of bed form movement. Then going to the right, you can see a whole series of more thinly bedded units, and then the next diamictite D37 is at the right hand end of the picture. Moving in, this is what the bulk of this interbed 3 looks like. Extremely complex, very wedge-shaped bedding. No beds can be traced very far. There's cross-bedding going in different directions. There are ripple structures. There's laminated stuff. There's little channels. It wedges in and out. Very complicated stuff. A huge variety of structures being accumulated and a whole pile of little erosion surfaces, whole little wedge-shaped bedges just stacked on top of each other over a reasonable period of time. Now, the other thing that the eagle-eyed among you might notice is there are two kind of pink football-shaped things down at the bottom here, which are rather nice granite drop stones. So this is lovely. This indicates that we've got icebergs, we've got an ice margin nearby. The high energy of these structures we find within this particular interbed indicates strong conditions, probably strong tidal conditions, And there could have been an input of a lot of glacial outwash material, but the current conditions here are so strong that all that material would just get winnowed away, kept in suspension, and it's only these really big lumps of clasts that have actually been preserved to indicate that the ice margin is nearby. So looking at the logs from the two sections, I've shown you examples of the one on the right hand side, the west coast one. There's the big event bed at the bottom, eroding down 1.5 metre into the underlying diamectite. There you can see where the drop stones are. You can see some paleocurrent measurements and a lot of complexity. Ripples, cross-lamination, quite a lot of liquefaction structures as well. And then a sharp top at the top where D37 just cuts across. And here's Tony Spencer standing on that boundary at the top of this interbed with the next diamectite coming in quite sharply. So interbed 3, what can we say? Well, the scoured base with relief, a rapidly deposited event bed at the bottom. There are no megafaucets, different from the underlying two units. We've got a rather random arrangement of laminated, cross-bedded units. These look like tidal channels and banks, but all fairly low relief stuff, all fairly small stuff compared with what we've seen before. We see the large drop stones implying carving icebergs. Any evidence for finer glacio-marine input would have been removed, washed away by tidal reworking. And again, we can't say much for what happens at the top because the D36, at the bottom, or the top for that matter, but at the bottom, it's an erosional surface, so we can't really say what the significance of it is. Finally, interbed 4 at the top, just one outcrop of this. Here you can see quite thinly bedded units overlain by a quite thickly bedded unit. Let's look at the thinly bedded stuff. It's different again from what we've seen before in that we have some nice sheet-like units of cross-lamination. At the bottom you can see some very, very nice ripple bedding, and they're actually climbing ripples at the top. And the actual ripple forms you can see preserved on the top of the bed, buried under the orangey looking stuff, which is silt. And then the next unit, you can see lamination in it, and there's a nice little load structure hanging down from the bottom of it, maybe a loaded scour. But this implies that the silt underneath was fairly soft and soggy for the sand to sink down into it. And then on top we've got some low angle cross bedding with muddy drapes along the faucets going from left to right, as opposed to the bottom stuff at the bottom which is going from right to left. This gives a general impression that accumulation rates were fairly high and the sediment didn't have much time to compact between each unit accumulating. That's where we see these rippled beds. If they're directly overlain by silt, the silt can be eroded off and you can actually preserve the ripple shape. You can see here the faucets of the ripples advancing towards you. So the ripples have been migrating and then they've stopped sharply and been buried by mud, and they've then been exhumed recently. More rippling, more cross-lamination rather. Package here, this is about 30 centimeters thick or so, and at the bottom you can see the rippled surfaces, and you can see that this is a climbing ripple bed. These are a series of ripples that have been moving forwards and upwards as sediment has been rapidly deposited. And if you look carefully, the upper part of this is the same. So the ripples have been migrating, they then stopped and got draped by a few millimeters of sand, just draping the tops of the ripples, and then they've sort of started up again, and we've got a whole 30 centimeter thick package of climbing ripples. Now this implies very rapid deposition. So here the ripples are moving forward, but the sediment is accumulating at about the same rate upwards as the ripples are moving forwards. This kind of structure where we see these climbing ripple beds, we can work out that this bed would have accumulated in, half an hour or so, very rapidly indeed. So this looks like very rapid event beds, high suspended sediment concentrations and rapid fallout of sediment. One wonders if that is indicating an outflow from a glacier, perhaps. It's quite conceivable that that's the case. The other thing I've not illustrated here, but at the bottom we see a sort of soft, sloppy contact between the underlying diamictite D38 and this package. In other words, there's no evidence of subaerial erosion or periglacial activity here. It looks as if D38, as the ice retreated, was left underwater, and these deposits on top, this interbed, has actually loaded and sunk to form big load balls sinking down into D38. So this is a different type of transition yet again. The lower package up to sort of the 10-meter mark are sort of these thin cross-laminated or laminated beds. They look like event beds, in other words, things that are deposited as a sort of sudden storm or outflow. The central section are more cross-bedded units. There's been more reworking, slower rate of deposition, and then we've gone back at the top to more of these kind of event beds. Few current directions there as well. So again, this is a slightly different set of circumstances from the previous three cases. Only the bottom of this section is exposed. There's no evidence of subaerial exposure at the top of the underlying diamictite, but soft sediment infolding, implying continuous subaqueous conditions at the D38 interbed boundary. So it's almost as if the ice retreated, tide water glacier retreated, leaving shallow marine conditions, and the interbed here may be sort of, if you like, outflows from the retreating glacier deposited on top of the diamictite bed. So we have event beds indicating very rapid deposition from suspension, high sediment concentrations. These could be just normal storm layers, but one's slightly inclined to wonder whether we're looking at direct outflows from glaciers. The upper half shows more reworking. Perhaps we've got tidal currents again reworking all this material as we've seen before, and then a return to more event beds. I've just plotted all the paleocurrent information from these four cases. It's not exactly to scale, but that's not the point. What it does show is that it's complex. You're not getting a repetition from bed to bed of the same thing happening over and over again. The paleogeography in each case is different, complicated, and it's very difficult to draw any firm conclusions about what the orientation of things is from all this rather conflicting information. So a quick summary of what we might be seeing here. At the base of one, deep subaerial erosion, and then transgression up a valley, and then the next ice advance comes in, and then at the base of two, sea levels fallen. We've got subaerial exposure again with a shrinkage crack, periglacial, a frost wedging surface, but then a low energy transgression in this case, different from the first one, and then the next glacial advance comes in. And then we've got some erosion. We can't really say what the nature of the boundary is there, but we know we've got icebergs locally depositing large blocks. Any fine stuff may be getting washed away, and then the ice has come back again. And then we've got ice margin retreat, but possibly underwater, and maybe a little bit of winnowing, which is something I've not gone into any detail. So a repetition of shallow marginal marine conditions and glacial deposition, but slightly different each time around. Just to say a few things about the overlying members 4 and 5. They're only exposed on Islay. They lie offshore to the southeast of the Garvellachs, so we can't say anything about them from there. Member 4 outcrops are rare and small, and you really can't put them in stratigraphic contact. There's one big outcrop of interbed in member 5, but it's inaccessible. It's a cliff which you can't really get at. So this is why I've dwelt on the Garvellach examples. The Islay examples are very... There's one rather nice unit, and this is the one that everybody who's been to Islay will have seen. It's just opposite the ferry terminal. And there's this thinly bedded package between two diamictite units. Again, quite unlike anything I've described to you before. It looks as if the bedding is concordant at the bottom, but it looks slightly concave up, and then it's truncated by the overlying diamictite. This almost looks like a kind of delta 4 set, bottom set package would be my best guess. The problem is we don't really know what the stratigraphy it is. Tony thinks it's in member 3, but it's very difficult to be certain. Other outcrops we see, how about this? This is further north, north of the Carlisle distillery. Quartzites on a decimeter scale. You can see erosion, a little scour surface there. It looks as if that surface is truncating down through the underlying material. I mean, this could be a delta slope package, but it's very difficult to interpret this kind of thing from a small outcrop on its own without a larger stratigraphic context. It's very difficult to know what to say. And this is the sort of thing one sees a lot of. It's just a pile of quartzite. It's as bad as a pile of broken glass, really. You can't really see much in it. That is cross-bedding, and that's about the long and the short of it. This is the really good outcrop on the Sound of Islay at Con Tom. But when you get close to it, again, you don't really see very much. You see bedding, you see some convolute bedding, there are injection structures, there's all sorts of things, but it's very difficult to get an overall impression of the stratigraphic architecture. These rocks, if anything, they look rather like the Jura quartzite that Bruce Lavelle and his colleagues have recently interpreted as a tidal delta sequence in the Jura quartzite, the overlying Jura quartzite. And it may well be that's what we're looking at here, but it's very difficult from the outcrops we see in the Port Askaig to draw any conclusions. So, final thoughts. We're looking at a range of shallow marginal marine environments with tidal influence. There's more work to be done to pin this down more precisely. The 4 interbeds are different. The paleogeographies in each interval are different. The topography left by at the end of each glacial event was different. Relative sea levels are indicated, I've talked about those, but there's no evidence for large changes. We're talking about changes of tens of meters, but not hundreds of meters. And one wonders whether during the entire time the member 3 interbeds were deposited, was the ice margin nearby rather than the ice having melted away completely. Thank you.
Welcome everyone to this talk on the non-glacial geology, in particular the continental environments. So I'm going to be talking about the interdiamictite units, and I'm going to be talking principally about member 2, where the continental environments are perhaps best represented in the Port Askaig Formation. There are probable continental rocks in member 1, but I've not studied those in detail, so I'll be concentrating on member 2. Member 2 is shown here in this panorama on the southwest of the southwest coast of the main island, Garvellachs. It starts just above the jelly fluxion horizon, which is a major potential break within the sequence. And it's indicated here between the 2 red lines as being 150 meters thick. It's 150 to 160 meters thick across the islands. And it comprises a series of diamictite groupings, which are interbedded with distinctive brown weathering sandstones. Such sandstones are present in member 1, but they're thinner and more lenticular. These are extensive, correlatable across the islands and relatively thick, tens of meters. The member 2 is overlain by member 3. Member 3 being characterized by sandstones which weather differently. They have a different petrography, which is more quartz-rich, less dolomitic, and they weather distinctly white, whitish grey at outcrop. They're also thicker. And as we'll see later, they're interpreted as marine. So member 2 is in its context in the total Port Askaig Formation shown here. You can see the diamictite groupings, the interbedded brown sandstones, the fact that these brown sandstones are thicker than in similar interbeds in member 1, and that the sandstone interbeds in member 3, shown here in yellow, are whitish. White or white-grey sandstones, the more quartzose petrography, is definitely arriving into the basin during the member 2 times, but it's not as well developed as in member 3. We're dealing with diamictites 19 to 32, although diamictite 32 is only developed in the type section on the northeast coast of the main island. So if we look at the correlation across the islands, it's something like this. We can see in the red dashed line the correlation panel shown on the right-hand side of this picture. It goes from Garvellach, Arkuli, and then there's a Skealethacuin, which is actually missing from the map, but is in the position of the red arrow and in the position of the red arrow on the cross sections to the right. The cross sections show at the same scale a series of diamictite packages in brown with the interdiamictite units shown in white. Now I've datumed these on what seem to be the most sensible datums. It's not totally clear whether the tops of diamictites should be flat, but these datums give you a view with that caveat of what might be a reasonable set of paleo horizontal datums through this series of rocks. So the lower unit, D19 to D22, is really a diamictite complex. Diamictites are numbered from the type section on the main island, and this particular group is separated by very thin interbeds. I've indicated in red where the wedges, the emergence horizons at the top of the diamictites, which have seen freeze thaw, have been found. D23 to D25 is a very interesting group of diamictites, including significant stratified diamictites, we'll talk about later. D24 to D26 I've indicated as a group, so there's some repetition there with the group underneath, D23, D24 being repeated. And the reason for putting D26 as a datum is, as we'll see from Dilshad, this is a highly correlatable characteristic set of events which cross all of the islands, and which is almost certainly a flat datum, and it is also almost certainly an erosional unconformity. As you can see from this cross-section, the right-hand side seeing erosion, particularly of the significantly thick diamictite D26. D27 to D29 illustrate incision of a deep channel on Skealethacuin, the Skerry, indicated in red. And that feature is also seen in the package D30 to D31. So there's something funny going on at Skealethacuin, as you can see from the fact that we have uplift and erosion in the D24 to D26 section, and then incision in D27 to D29 and D30 to D33. Also should be pointed out at the very top, there's deep incision below the base of member 3. This is 30 to 40 meters deep incision across the islands, infilled by thick white marine sandstones, which will be discussed in the marine talk. Okay, if we contrast that with the section on the island of Islay, you can see here's a correlation of member 2 between the red lines, and you can see that the proportion of diamictite is much greater relative to sandstones, and you can also see that there's a member 2 comes almost to rest on the subjacent rock units, in this case the Losset Formation. So there's if you like an onlap, or what looks like an increase in accommodation space during the formation of member 2 with respect to member 1, but nonetheless it looks as if Islay is relatively high because the diamictites are becoming even more amalgamated than they are on the island, on the Garvellach Islands. So there's a distinction which indicates that there's a substance control on the formation of member 2, more substance perhaps than member 1, and perhaps less than member 3. We'll see as we go through member 2 that accords with the sedimentology, that substance is probably increasing, accommodation space creation increasing throughout member 2. Okay, let's have a look at some of the facies. We'll start with the fine-grained and work our way up to the coarse-grained. The fine-grained rocks are all phyllites, so it's difficult to work out the original grain size, whether it was actually silt or mud. In some cases, you can see from the amount of sand that's interbedded that it's more likely to be silt, and in other cases, it looks as if it's more likely to be mud, but they are, of course, recrystallized because these are greenschist facies rocks. What we can see in this panel of 6 photographs is that we've got abundant soft sediment deformation in laminated siltstones. We've got a fair amount of dolomitic material in the fine-grained units, which weathers brown. And sometimes that's interlaminated, particularly in the siltstone or the fine sandstone beds, the coarser component. And it's also commonly rippled, shown in C, ripple laminated dolomitic siltstones. Some of the ripple laminations are clearly soft sediment deformed with thrusting and microfaulting, as shown in D, and that's attributed to minor slopes, which are sliding in all sorts of directions. The directions you can't actually measure because a lot of the soft sediment deformation features have been rotated into the regional cleavage. We have laminated siltstones with dropstones. This is a transitional facies from stratified diamictite very often into the interdiamictite units, indicating a passage from glaciogenic rocks to non-glaciogenic rocks. And then at the very top of member 2, we have rhythmic lamanites, which appear to have been drilled here for paleomag holes. These are soft sediment deformed as well, but these are millimeter thick laminae of very fine sand and silt, and there are something like 2,500 of these which were measured in intricate detail. Slightly coarser facies, we go up into rippled sandstones. The ripples are interesting. They are, as you can see in figure A, commonly combined flow ripples. These are erosional ripple forms which are symmetrical and some cases trochoidal, indicating wave orbitals eroding the ripple form rather than a current which is forcing the ripple to migrate in a particular direction. So these are combined flow ripples. We have symmetrical wave ripples on bed surfaces. The best developed ones occur on a series of surfaces just above our datum, D26.41, across all 4 islands. We have climbing ripples, shown in the picture with the hammer, number C, stosside accretion. These are very low angles of climb, but they are climbing ripples indicating a high aggradation rate. That's actually in a medium sand. And then in D, we see more syndepositional faults, sediment moving around while ripples are migrating. In E, we see aggradation of climbing ripples in phase upbuilding, and we see that also in F. This indicates a high rate of bed aggradation. So we've got current energy combined with wave energy, and we've got high rates of aggradation indicated by the ripple climb. Not unexpected for facies associated with glacial environments, it has to be said. In terms of the sandstones, picture A illustrates the difference in color that I've been talking about. There's an extremely brown colored sandstone in that picture, interbedded with more gray colored sandstones, and that's characteristic. And the brown sandstones, when you smash them open, they're actually gray hearted, as are the gray sandstones. But the brown sandstones have got more dolomitic material and often quite poorly sorted dolomitic material within them. That's a detrital dolomitic material. Sandstones are normally cross-bedded, both the dolomitic ones and the grey weathering ones. There are also fine sandstones which are infilling the wedges, and sometimes these can be related to a capping of fine sandstone on top of a diamictite, as shown in C. It's possible that that's windblown sand. It looks as if there's a lag there developing on top of that diamictite. Sand which is blowing around on the landscape surface is then falling down into these wedges. In D, we can see some of the poorly sorted dolomitic sandstone. It's a distinctive facies with angular dolomitic material, probably derived from diamictites which have eroded dolomites in member 1 and it's been recycled. But it's also possible that somewhere on uplifted blocks, maybe more uplifted than Islay, member 2 is still cutting down into subjacent stratigraphy, pre-Port Askaig stratigraphy. The dolomitic sandstones are relatively poorly sorted, as I said, and sometimes they have top surface lags, as shown in F, which indicate either wind ablation or current erosion, collecting the coarse grained lag material on a top surface. Okay, the grey sandstones are pretty normal for sandstones. They're typically decimeter bedded. They're often tabular to planar tabular crossbeds. Trough crossbeds also occur, but there are a lot of tabular ones. There is a small amount of liquefaction with liquefaction anticlines and synclines. This is useful in that it allows us to see which rocks were deposited relatively soon after others. And in some cases, you can see that the tops of the diamictites are clearly liquefying and overlying sandstones are being passively deformed on top of a liquefying diamictite, which indicates that the transition between the diamictite and the interdiamictite unit is relatively fast. At least the diamictite was not fully consolidated and it was dewatering. In D, we can see that there's plain lamination as well as cross-bedding. Plain lamination is quite well developed in decimeter beds and particularly characteristic of small coarsening upward sequences, as we'll see shortly. And then on the right-hand side, we can see that there are also some massive sandstones where we don't really see any structures at all, and that's particularly true of the more dolomitic ones, actually. The grey petrography seems to be heralding the incoming of the white petrography in member 3. I won't go into petrographic detail, but a lot of that is in the memoir. Okay, conglomerates going one grade coarser. We have conglomeratic bed armors developed, in this case on top of D26. There's a beautiful surface on the northeast of the main island. This indicates current reworking, which has winnowed away the silty sandy matrix of the diamictite and left a bed armor. We have frost shattered stones. There's a simple one here. It's just been wedged open at the tip of the pencil there, and then not subsequently moved. So any transgression on these bed armors is actually relatively gentle. These frost shattered stones have not been displaced one from the other. That's an important point. In Fascie C, we see some laminated siltstones. Actually, these are laminated sandstones. These are rhythmically laminated sandstones, overlain sharply and erosively by a poorly sorted conglomerate, clast supported conglomerate. We also have matrix supported conglomerates as shown in D, which are interpreted as that particular bed is the one example we have interpreted as debris flow. Okay, so taking the facies and putting them together into facies associations, the first facies associations are these moderately well-sorted sandstones, and these commonly have steep erosional bases, the most dramatic of which is shown in C. This is not the best picture of this outcrop, but it's actually a 5 meter deep cut. The bedding is shown in red, and the erosion surface below the main sandstone is shown in yellow. And this is one of a series of extremely steep bank cuts in this area on the southwest coast of Akuli, which indicates rapid cut and fill below these sandstones. They're tabular cross-bedded, occasionally liquefied, as we've seen. They form in units up to 5 meters thick, almost pebble-free in many cases. So the pebbles, when they do occur, are in these interbeds of dolomitic brown sandstones, which are discrete events. So this looks like a petrography which is either distal from a glacial source or nothing to do with a glacial source. It's certainly been it's certainly much better sorted than you would expect from proximal glacial debris. And possibly this is the extrabasinal material which comes to dominate the basin much later, or much higher in the section, we don't know how much later, of course, in the Jura quartzite. This is a drone image from Jordan and Doug, which illustrates where picture C in the last photograph with the steep downcut was taken. And it also indicates in a dashed yellow line another such downcut further inland, cutting down into the diamictite D25. And you can see that what we've done is we've measured sections through these entire stratigraphies on the island, and we've found our datum, the D26.41, and we'll hang those sections on this datum. But this illustrates the use of these drone images in, if you're working in inclement weather, it's extremely nice to be able to go back somewhere dry and follow the beds that you've just logged with the data from these drone images. The second facies association I'd like to talk about is, I think, very informative. It's a series of coarsening upward sequences. These are typically 2 to 3 meters in size, not particularly thick. You can see a nice example here, which is near the sheep pen on Islay and Neve, the Holy Island. And it starts off, as is typical, with a dolomitic laminated siltstone that's probably got ripples, and it's almost certainly got soft sediment deformation in it. And that coarsens upwards into a fine to medium interbedded rippled sandstone, which is grey, and then into a plain laminated decimeter bedded medium sandstone with the notebook on top of it. And that coarsening from dolomitic silt through rippled fine sand into continuous medium sand with plain lamination is distinctive. It's correlatable at this particular horizon, but it's also found throughout these sand interbeds. And I would interpret this as deposition from, rapid deposition from suspension in a minor mouth bar. So we're dealing with a prograding unit, hence the coarsening upward. We're dealing with rapid deposition in plain bed conditions, and some of these units are overlain by erosional sandstones or even conglomerates, as we'll see later. The right-hand side, you can see some detailed images from bottom to top in this section, illustrating the points I've made, the dolomitic siltstone, the current ripple lamination in the middle, and then this plain lamination, draping plain lamination at the top with indicating a relatively high degree of bed aggradation. Here we see a log and a section from the same island, which shows such a coarsening upward sequence, starting at the yellow horizon, which is indicated in the log. This particular one has a series of sedimentary faults faulting down to the left, which have been picked out subsequently by quartz veins, and they're shown in blue. These are decolling on a siltstone horizon in the cleft in the rock, which is indicated in thick black on the log and on the photo. And this coarsening upward sequence passes up into a conglomerate lens, which is outlined in red. So here we've got a minor channel, which is carrying conglomerate, which is prograding over its own mouth bar, which has got syndepositional normal faulting as it moves into the basin. And that sliding or slumping of the minor delta front is typical, particularly of the lower facies, the dolomitic siltstones, as we saw in the pictures of the lamanites. Here we see a third facies association, which is the same but bigger. So what we've got here are coarsening upward sequences. This is from the southwest end of the main island. In the lower part of the main diagram, you can see a blue triangle indicating a coarsening upward sequence, which is also shown on the log on the right-hand side. This is of the sort I've just described, facies association 2. It's about 3 meters thick, passes from a diamictite directly at D30 into a laminated siltstone, rippled siltstone, plain laminated sandstone. Then there's a second coarsening upward sequence, which you can see in the cliff profile quite nicely, if you conceive of that as a gamma ray log. And you can also see it in the log on the right, which is measured on the foreshore rather than in this cliff. but the correlation has been walked out along the black and the red horizon. And the upper part of this sequence consists of a multi-story stack of poorly sorted, fining upward, massive to liquefied sandstones with top surface winnowed lags at the very top. So what we've got here is again a prograding sequence overlain by channelized fluvial deposits, and I would interpret this as a slightly thicker deltaic mouth bar. In the log, you'll notice a load ball, which is about a meter in diameter on the foreshore. So there's, again, rapid deposition, dewatering, and sediment sliding on these mouth bars. This is the same outcrop with an orthorectified drone image, which is absolutely fantastic, actually, for correlating between the vertical cliff and the horizontal foreshore, which otherwise is a bit of a nightmare, to be honest. And here I've put our logs against this, but again, just to illustrate that the drone images allow us to do this bed by bed correlation with a lot more certainty than is possible at the outcrop, sometimes at least. Okay, the continuing with Fassi's association 3, this is perhaps the most dramatic example. What we see here is a incised conglomeratic body shown in red, which is cutting down into subjacent rocks on the island of Scialetha Cuin, the Skerry. The section begins with D30, which is actually a partially liquefied top of a till. Sorry, a diamictite, I should say. Probably is a till. And then we have overlying that dolomitic siltstones. They're shown in picture C. These go up into green laminated siltstones. And again, soft sediment deformation, unfortunately folded into the cleavage, so we don't get a direction. Above that, we see the distinctive parallel laminated sandstones again, of part of the coarsening upward sequence at locality D. And then we pass up into a conglomerate, the main conglomerate body. So what we've got here is, I think, erosional incision of at least 2 channels, the lower red unit and the upper red unit separated by the yellow interbed of sandstone at D, which have actually incised into their own deltas. So if I've got a delta which is only 3 meters thick and I've got a channel which is 4 meters thick, then I don't see the delta anymore because the channel incises it completely. But what we've got here is that happening, but a little bit remnant of the delta front being preserved by the erosional incision of the overlying river deposit. So, okay. Now, if we look swiftly at the diamictites themselves in member 2, I want to make points about the transition between, or the relationship between the diamictites and the interdiamictite units. Some of the bases of the diamictites are erosional. For instance, D19 erodes out the magnetite-bearing mudstone at its base. So there's mild erosion there, for example. There's a significant erosion below D26, and so on. At the top surfaces of the diamictites, how do they transition upwards into the interdiamictite units? Well, sometimes we find these pebble lags, such as A, so there's some reworking going on. Sometimes we find residual material, frost-shattered material, which has not been removed, as in B. You can see a sort of halo of bits of feldspar out of this granite clast, which have not been significantly removed away from it. So this is gentle, perhaps even aeolian ablation of material from the top surface of a diamictite, but certainly not, let's say, a high energy transgression. In some cases, as in C, the wedges are preserved, and in this case and in others, the sandstone which is feeding the wedges can also be observed at the outcrop, indicating that fine material at the very top of the frost-cracked diamictite surface has not been removed. So the point I'm making here is yes, there is some current reworking, but there is also evidence for a very gentle passage, non-erosional or just simply a low energy transgressive surface up into the overlying siltstones of member 2. In D, we see a siltstone interface between two diamictite units, in this case D24 and D25. It's just a very thin intercalation of siltstones and sandstones between those two diamictites. In E, we see the stratified diamictite D25 on Holy Island, and a close-up of that is shown again in F. And this passes up into laminated mudstones with dropstones. You saw a picture in the Fassi's photograph of the lamanites. This is a gradational upwards passage from a stratified diamictite into a laminated siltstone and mudstone, which is then passes upwards into a coarsening upward sequence, which is incised by grey sandstones. So the conclusion I would draw is relatively minimal erosion at the top diamictite. So low energy passage between diamictite and interdiamictite units, preserving the periglacial phenomena at the top of the diamictites. This is an example of a log section from that place at the top of D25, showing that transition into a coarsening upward sequence up into sandstones. So we've got a stratified diamictite deposited in a standing body of water. Standing body of water then becomes, as the ice retreats, it becomes site of deposition of laminated siltstones with isolated pebble granule dropstones, the ice margin becoming distal, and then a delta progrades into that same standing body of water, which is fed by a river, which is fed by mature grey sandstone, which is possibly non-glacial, possibly extrabasinal, but not glacial material at all. This just shows we've done our homework. So this is a zoom out of all the sections that were measured on Holy Island around this interval, showing this transition between D25 upwards into its minor mouth bar, and then incised by grey sandstones, and then subsequently by brown sandstones, brown dolomitic sandstones, up to our datum horizon of D26.41. Dilshad will take that D26.41 datum apart in more detail in a separate talk. It's well worth examining in great detail because there's so much going on at that interval. One of the things that's going on there is that there is a correlatable unit of wave ripples across all the islands, all the sections in all the islands, just above that datum. And for me, this is probably the largest extent that we can prove of a single water body. It's about 5 kilometers. The wave ripples have various strike orientations. They're not all consistent, but they are occurring at the same level. So here we've got obviously a wind agitated water body which is moving sediment on its bottom, and that then subsequently gets infilled by one of these minor deltas with a fluvial channel. So coming back to the datumed cross sections, what we've also can demonstrate here is that the paleocurrents are coming from all over the shop. So if you look at the rows on the right hand side, we've got strikes of wave ripples. We've got strike directions of those are classed orientations, and then we've got paleocurrent roses. So currents broadly flowing towards the northeast, but actually all over the place. And there's really not a lot of rhyme nor reason in any particular stratigraphic interval. Those are taken from the interval from D22 to D26.41 in this diagram. What we can also see is we've got uplifting and erosion, as we saw earlier on the right-hand side, the southwest end of this diagram. I relate this to tilting related to syndepositional faulting. I think that looks to me like an upward tilted footwall block with some fault system which is down throwing to the right-hand side of this diagram. And then as we go up through the datum cross-section, more paleocurrents, opposite direction. So there is a difference in this sense between the uppermost unit and the lower unit in terms of a predominance. But paleocurrents basically without systematic orientation, even over the short distances and in the short stratigraphy. And that for me indicates that this is a complex environment in terms of its geomorphology. Downhill was in many different directions in many different times. The stacking of the channels at Sgurlletha Cuin I would relate to pinning of the drainage system by the syndepositional faulting. And we'll explore that story when we go to Sgurlletha Cuin in a virtual field trip in subsequent talk. There are two major conglomerate bodies on the island. The lower one in B is the debris flow, and the upper one in A is the one we've discussed before, which is this series of incised fluvial conglomeratic channels. So this is the argument for why Sgurlletha Cuin is a special place, and there are actually 5 stacked incisional features on the island at different stratigraphic levels, which is a hell of a coincidence and caused Tony major correlation headaches. But we think we've got it worked out now, and it's a special place, I would argue, because the drainage is being pinned by the syndepositional faulting. So what does this depositional environment look like in the interdiamictite period? Well, I've selected this diagram from the Mackenzie Delta, which shows a periglacial landscape, and it's near the sea, which is up to the left. That's the Arctic, and it's got sediment-laden rivers, which are brown coloured because they're sediment-laden, and it's got lakes which have access to the sediment from those rivers, which are also brown, and other lakes which don't have much access, which are temporarily at least separated from river supply, and those are more blue. There may be a sun angle effect in that, I'm not totally sure. But you can imagine at least that some of these lakes are better connected to the clastic source than others. And I've indicated in yellow the direction with which the river supply enters the lake. And you can see it's all over the shop. So some of those are pointing towards the sea, and some of them are pointing towards the land, and some of them are going up, and some of them are going down. And that's by virtue of the fact that these lakes are relatively small. I've indicated the Garvellachs Islands in red. That's a 5-kilometre long box. So that would be, all of the islands would be in that box. And you can see that one of these lakes, for instance, the one with wave ripples above D26.41, is about the right size. And I think we're dealing with a landscape shaped by the geomorphology of the diamictites, which almost certainly had erosional relief and also unfilled accommodation space in the subaqueous diamictites. So we've got a composite, a complex relief surface with a fluvial drainage system. My guess is that there were actually different drainage systems at different times. So when at times of ice advance, there would be a glacial related drainage system, and at times of ice retreat, there might be a basinal, if you like, drainage system, bringing in the more mature petrography, which eventually comes to dominate the basin in the Jura quartzite times, but is at this time a subsidiary source. So that would be my summary of the continental environments. Now, I have to make the proviso that I have no way of telling whether or not these lakes are actually lakes or marine embayments. I can't say much about salinity. The presence of dolomite is in part due to detrital dolomite in the fine-grained sandstone grain size range in particular. There's also, but the dolomite is recrystallized, and determining what is diagenetic and what is detrital is not possible. The fact that there is dolomite suggests marine waters are nearby. Whether those are pore waters or depositional waters can also argue. Lakes or embayments, one of the two. I'll leave it at that. Now, thank you very much for your attention, and happy to answer questions if I can. Welcome to this virtual field trip to Sgurlletha Cuin. We'll look at member 2 rocks exposed on this island. The island is situated in a strait between Akuli and Holy Island, and it's difficult to access. You need good conditions of swell and low tide in order to be able to get on the island, and for that reason, even though it's beautifully exposed, there's still actually quite a bit of work to be done here. As we spin round, you can see that the island consists of two main parts. There's the grassy knoll towards the southeast. We come round now to look down dip, and then there's the intertidal seaweed covered part of the island towards the northwest, sorry. And as we turn round, you can see the bedding. There are two groups of diamictites, D24, D25 in the black rocks on the right now, and then D27 to D30 in the green grass covered slopes on the higher part of the islet. We're now flying down stratigraphy to look at D24 at the bottom of the sequence. This is not particularly well exposed. It's a slippery seaweed covered islet. You can see it here looking along strike back towards Holy Island. It's a massive diamictite. D25 in the bluff here is more interesting. It's a stratified diamictite. As you can see, here's a close-up showing the granular to small pebble sized material and the stratification. And this passes up into a lacustrine succession characterized by a beautiful wave rippled surface, thin bedded laminated dolomites and ripple cross laminated fine sandstones. This is a facies association too, and these pass upwards in an irregular upward coarsening through these rippled laminites into this spectacular conglomeratic body. This is where you'll find most people clustered on the islet, typically when we go there. There was Doug and Tony. This is a debris flow. It's a matrix-supported conglomerate, extends right across the island and has been correlated in detail. And above it is a diamictite unit, D26 prime, which is not the main D26 unit, which is eroded out on a coulee island to the northeast of us. At the top of that diamictite, you saw there a beautiful granite clast with the crystals dragged out of it by shear deformation within the diamictite. The base of D26 prime is shown in detail in some rocks that we're now going to go and visit on the other side of the islet. This is near the waist of the island, which is poorly exposed. Here we go, we're coming in now to the top of, to the base of D26 prime. This is a grounded diamictite which includes shear fabrics at its sharp planar base, as you can see in these photographs. Now we cross the waist of the islet, we clamber up the steep bluff of D27 to D30, a composite diamictite, and we look at this unit, which is a conglomerate cut down through laminated siltstones and dolomites, as you can see beautifully folded here by the notebook. This is an incised fluvial conglomeratic channel, sandy in part with crossbeds, and it's incised into an upward coarsening sequence which is very poorly preserved, but you can find here in the grass by this crack which leads through the center of the upper conglomerate body between D30, D31. And this conglomerate is as a grain supported fluvial conglomerate, and again can be mapped out in detail, and you've seen pictures of that in the slides. And here's Roger measuring clast orientations, get some paleocurrent markers from aligned pebble trains in this conglomerate. And now we go to the far side, the northeastern wing of this conglomeratic material is poorly sorted. There you see Tony's stick pointing to the base of the conglomerate. And this view gives you, I think, a nice view of the overall geometry as we fly back over this ridge, roughly along the boundary between the conglomerate and the underlying diamictites. Oh, that was it. Time to leave the island. Alistair must be coming back to pick us up. So that was Garvellachs, a small but beautiful outcrop
Well, wonderful. Thanks very much, Bruce, Doug, and the other presenters, Ian, Roger, as well on that session. I'm going to get into the Q&A. We've running a little bit later than I planned we're about 10 minutes behind, but I will just let the Q&A go on. We may delay the start of the last session by 10 or 15 minutes just to get some of these questions answered at the time. I'm going to start off with Paul. Paul's over in British Columbia, I believe. Do you want to just talk us through your first question about ice-water equilibrium fractionation? It's way above my pay grade.
Yeah, so the question concerns whether the heavy oxygen isotopes require evaporation. Incidentally, the hypersaline Dry Valley Lakes in McMurdo are actually not heavy in oxygen isotopes. They're the same composition as the meltwater sources, and that's because you don't have very much evaporation there. It's mostly sublimation. And so when you have sublimation of ice, the sublimation is quantitative. There's very little fractionation because of the ice is solid. However, when you have snowfall, you have very strong fractionation because of the cold air. So in the snowball situation, the marine ice is heavy to begin with because of equilibrium ice-water fractionation. So it's 3 per mil heavier than the ocean. And then when it sublimates, the water vapor is the same composition of the ice, but the snowfall is very heavy. So the coastal ice is going to be very heavy, and meltwater derived from it will also be isotopically heavy. So in that case, you can get heavy oxygen without evaporation, although it might be hypersaline through sublimation.
Over to you, Ian, yeah?
Yeah, I mean, these are very interesting theoretical arguments, but if you just take the simplest interpretation, is that you've simply got a cold marine dolomite. You don't need any other assumptions about what's going on. And as I presented later on, I mean, up until recently, I was really thinking in snowball terms. I thought that unconformity could well be a snowball unconformity. But in the last couple of months, I've just switched around. And I think that the Sturtian glaciation may well not have been a snowball in the sense that the Marinoan was. So, I'll pick that up a bit later. So all I'm saying is that it's the simplest interpretation is just that it's the cold. You don't need any theoretical arguments.
But then how do you explain the sandwich polygons? Because the sandwich polygons require a very strongly seasonal climate, but you're only at 22 degrees latitude. The easiest way to explain that is in a snowball Earth, because in a snowball Earth, because of the solid surface, you have very strong seasonality everywhere.
No, but my point was, what I was talking about there was the Svalbard succession, which is entirely glacier marine. And what I was doing is to show that a cold glacier marine precipitates can occur. And I'm then, by analogy, saying in the Port Askaig Formation, if you're getting concretionary carbonates, one can also interpret those as cold glacier marine.
But if you do not have a snowball Earth for the Sturtian, Port Askaig, first of all, you have a difficult time explaining the 56 million year duration, but more directly, you have a hard time explaining the sandwich polygons in the Port Askaig.
Yeah.
Because they're hard to make those at very low latitude.
Okay. I'm not going to address the sandwich polygons, Paul. I think I'd like other people to talk about that. We know that there's been a very substantial literature from people who don't like the application of the snowball, in particular the Sturtian, and I expect we'll hear more from those people later, but let's just leave it there for now, and then we'll come back and have more discussion later.
Okay, is that okay at the moment? We are going to talk about environmental change as the main focus of session D, and the final discussion we can pick up some of these points again. Paul, while you're on, you had another couple of questions later on about the secular trend in source rocks from intrabasinal to extrabasinal, and something about ice margin advances and retreats. Maybe you could just talk to it. Maybe it's Roger or Bruce, maybe to answer your question.
Right. So the first question concerned the change in the source material stratigraphically upwards through the formation with intrabasinal, quote unquote, mostly Garvellachs derived material at the base, and then the introduction of more and more quartz, sand, and granite stratigraphically upwards. So my question is, does this represent an expansion of the area of the ice sheet, or progressive downcutting of overdeeps, cutting older and older material, perhaps with onlap, up ice? And then my second question was, do you have any strategy to try to disentangle alternative explanations for the ice margin advances and retreats? The first being that they're externally forced by, say, orbital forcing or by tectonic forcing. An alternative to that would be from autonomous ice dynamics, from ice sheet surges, for example, which are common in polythermal glaciers. Do you have any strategy for trying to distinguish those alternative explanations for the very prominent ice margin advances and retreats that are observed in the Port Askaig?
Should we ask, maybe Tony can look at the first part of the question, the first half question. Tony, you there?
The source material, again, Paul, we're not giving you all the information we have. There is a feeling that the white sandstones have come from an entirely different source to the glacial material. In the memoir originally, there was fairly sort of well hidden stuff about chessboard albite, which occurs in the diamictites, whereas microcline does not occur in the diamictites, but occurs in the white sandstones. So we think, but we still haven't got to the bottom of the matter, that the sandstones will perhaps have the white sandstones will have a different source from the diamictites. So that's one story. Another story is the intrabasinal clasts in the diamictites versus the extrabasinal clasts in the diamictites. Your suggestion of did the ice expand might well be very worthwhile and sensible, but it's fair to say that the nature of the extrabasinal stones, which first appear in diamictite 15, really they don't change in nature right up till you get to diamictite 47. So from an extrabasinal suite, we don't really see an evolution.
Yeah.
We don't see an evolution of extrabasinal suites, let's put it that way.
You know, that'd be more consistent with overdeeps as a source, excavating down to the basement.
Right.
Up ice.
Yeah. Okay, that was me.
Okay, so the second half, I know Ian's done some work on cyclicity and Milankovic cycles in Svalbard in the Maranoa, and maybe you just take a look. Can you answer Paul's second question there, Ian, at all?
Well, in the Maranoan, we had arguments from modelling that suggested that precessional cycles could be important. We also in Svalbard had an underlying formation with 200 cycles that we referred to as precessional and used to estimate the time gap between the two and glaciations. But it seems to me that the Port Askaig is vastly more complicated and less easy to interpret in those terms, and therefore to make the distinction that Paul is hoping that we can make. So I suggest, could you ask one of the glacial people in the team if they could respond, David?
Yeah, I'm happy to.
Doug, yeah.
I'm happy to add a couple of words on the climate versus surges thing. That on the basis of the evidence on the ground, I see no evidence of surges and lots of evidence of climate change. The surging glaciers typically have a very, very high end glacial and supraglacial debris load, which is connected to ice tectonics. And so typically subglacial associations are then overlain but by a package of sediment deposited during the melting of the ice. And in the Port Askaig, it's extremely rare to find evidence of englacial or supraglacial debris superimposed on a subglacial sequence. All the indications are that the ice was actually rather clean. So on the basis of the glacial deposits, I would say there's no evidence requiring us or pointing us in the direction of surges. Secondly, in terms of the nature of the interbeds, it's quite plain that in a number of instances, the glaciers have gone away in between the ice advances, in terms of the nature of the sediments and the provenance and so on. And so we clearly do have multiple occasions when glaciers are arriving in the area and then withdrawing completely, which again is not really consistent with surge cycles in which the glacier is usually close by while it builds up to the subsequent surge. So my money's definitely on a sequence of climatically driven glacial cycles.
Yeah. And although Guillaume Leire only did not find precessional forcing at low CO2, longer period orbital changes might still be expressed. I mean, he only experimented with precession. So it would be a mistake, as some people I think have done, to say that at low CO2 in, say, early snowball stage, you wouldn't have orbital forcing. You could still have eccentricity forcing.
Yeah, I think that's a reasonable conjecture. Yeah.
Okay, and I'll just leave that one there for the moment. We'll obviously come back to some of these things later on. I want to just cover a couple of questions together. Graham Shields has asked about something that Ian had mentioned earlier about the Dolomites in Member 5 being a deep water deposit, which Ian is believing is representative of a Sturtian cap. And Matthew's questions about the Bonnehaven Dolomite, which is traditionally regarded as the cap to the Port Askaig, or has been regarded for many years as the cap, so which is very clastic rich sequence. And maybe Ian, you could just summarize your thoughts on the D45 Dolomite and the Bonnehaven Dolomite in terms of cap carbonates for everybody. Thank you.
Yes, I had to mention this Member 5 Dolomite in the context of the Dolomite talk, but actually as a team we haven't reached our final conclusion on what's going on in Member 5, and so I've still got to convince one or two members of the team about what I think is going on there. The Bonnehaven Formation, which overlies the Port Askaig Formation, is a consistently shallow water deposit. It's peritidal. That contrasts with the cap carbonates that you see on the diamictites, other Sturtian diamictites around the world, which are quiet water, deeper water settings invariably. So I had actually never claimed that the Bonnehaven was a cap dolomite. I just hadn't commented on it. And I didn't know that these Member 5 Dolomites existed. They just were mentioned in passing in Tony's memoir, because the best exposures of them are in these large fallen blocks, but there's no doubt at all the fallen blocks have come from the cliff behind. And the fallen blocks show a whole variety of features, and study of section samples and so on shows that the Dolomites are actually very, very different from any other Dolomite that we've seen in succession. They show turbiditic finding upwards cycles, and they're very extensively broken up. The substrate was incredibly unstable, which would be consistent with nearby seismicity. And the D45, D46, described originally as diamictites, are texturally pebbly sandstones. They've got sharp bases, they've got rafts of this dolomite material within them. So I'm thinking of them in terms of sediment gravity flow, but one that might not have been in very deep water and was probably quite close to bounding faults. And Roger in his talk talked about the Bonnehaven fault potentially moving during this time, and there are other faults further west that we think are active during this time. So it's a very special situation. It's nothing to do with the bulk of the Port Askaig story. It's just something at the end of the story, and it's something that we as a team have not yet discussed and agreed upon.
Yeah, just to prove we're still working on it, this is a sample of D45 that I collected yesterday or day before yesterday. There's a nice brecciated dolomitic horizon from the shores of Sound of Islay that I picked up. So I'm about to post a chunk of this to Ian to get some carbon isotope work done on it.
Thanks, Ian. I switched off my camera because my internet connection's not that great. But, could I just follow up and ask about the organic content, or we don't know? Because that's the other thing about Sturtium caps, is they tend to be organic, more organic rich than Maranoan caps.
Yes, I think they probably are, but I haven't got any measurements of organic carbon content, but the samples are available if someone would like to do so.
Okay, good answer.
Thanks, Graham. Can I just move on to Tim Holt-Wilson, who's asked a question for Roger, so we can give Ian a break there for a minute, and he talks about thicknesses of marine clastic sediments, and it's really a question, I guess, about the rate between sedimentation rate and subsidence rate. Are you there, Roger?
Yes, can you hear me?
Yes, we can.
Yes, well, it is clear that one of the special features of this whole area is what would seem to be a relatively complete sequence, because there is rapid subsidence, and that subsidence certainly is going from the Port Askaig times right through up to the Jura quartzite. You've got nearly 7 kilometers of material there of shallow water terrestrial stuff. And this is why I was talking yesterday about the kind of basin position of the Garvellachs. You have to imagine it being in the center of a basin that went down really pretty consistently. I have no idea what the number is. If somebody can give us some other dates within the Dalradian succession, we can get an idea of subsidence rates. But typical subsidence rates in sedimentary basins are sort of 100, 200 meters a million years. So, you know, if you're looking at 5, 6 kilometers of subsidence, you do the maths. It depends what figure you take. It's not impossible to find subsidence rates getting on for a kilometer a million years in some extreme sedimentary basins. But sure, the variations in thickness of the Port Askaig tillite across the outcrop belt must be a consequence of different subsidence rates. And it's just that in the Garvellachs, we've got a particularly fast subsidence rate. I don't know what that is. 200 meters a million years would not be fast on a sort of worldwide comparison. And that would only give us sort of 5 million years. So you don't have to have a long time for the Port Askaig formation if you have the fast subsidence. And clearly, to get these sequences where you get, you know, deltaic sequences and you get terrestrial things preserved, you have to keep moving the whole system down the downward escalator the whole time. Otherwise, you just get a whole pile of disconformities with lots of thin sequences and a lot of huge time gaps. The other consequence of this is what is happening to sea level. And of course, the interesting thing that we really wanted to know when we started all this is what happens at the bottom of the Garvellach succession. And it does seem to be transitional with the shallow water carbonates underneath. So that means if there was a fall in sea level, and we think of a worldwide glaciation as producing, you know, hundreds of meters of sea level fall, well, the base level in the area must have gone down at the same rate, because there's no great stonking great subaerial unconformity at the base of the Port Askaig tillite. It seems to be traditional. But exactly what those rates are in terms of rate of sea level change and rate of subsidence in terms of meters per million years or meters per 1,000 years for sea level change, I would love to know, and I'd love to know if there's any way of getting a handle on that. You can do calculations, but it's guesswork.
Yeah, thanks, Roger. Can I just, Bruce, have you got any extra comments on this? Because I know this is a particular interest of yours.
Yeah, no, I think Roger expressed it very very well. I mean, and you made the point yesterday that we have a composite stratigraphy which is 20 kilometers or so, but let's forget that. And I'll show a diagram which I'll have to apologize for in advance because I didn't forget that. But you know, the sequence in any given spot in the Dalradian is going to be significantly shorter. But nonetheless, there is a problem with the rates. If we take the global Sturtian duration and the implied rates for a rift to passive margin sequence, then something has to give. I think either our understanding of the basin is wrong, or the global duration doesn't apply to this area in its entirety. But I think it's difficult to square that circle. And then the other thing I'd say is that I think, you know, Roger's work I think points this out, is that there are sub-basins within the Dalradian which see the same sequence of events in terms of carbonate glacial sequence and a thick quartzite on top. But these are not necessarily the same basin. They're correlatable packages of events, but they're probably from Ireland to the Banff coast, you know, 3 or 4 different sub-basins which are involved in this whole thing.
Okay, thanks, Bruce. I will cut that one off now, and I'm going to let this go on for another 2 or 3 minutes, and then we're going to stop at 14:15. I've got Max. Maybe you could just unmute and talk your question about comparing the Sturtian of Port Askaig with the South Australian section. You've got quite a long question there. Maybe you could just summarize it, and maybe Ian or Tony can come in on that. Yeah.
Yeah, thank you. Yeah, just quickly, I guess this is actually in a succession that I know that Ian's seen because I was there with you in 2017 in Hololena South. There's I remember there's quite a lot of dolomite in that succession. Some of the dolomite there appears to be I mean, some of it is clearly detrital, similar to what you described in your talk in detail, but yeah, some of it seems to be orthogenic at least. You know, there's some of these finely laminated dolomicritic horizons, which they preserve fine scale sedimentary structures that clearly show that they were sin depositional, have been reworked and things like that, and that they lack detrital cores or any evidence of mechanical reworking. So also they seem just in appearance quite different to the underlying Burrow group carbonates, and this is sort of supported by the isotopic work similar to what you described in your talk. So yeah, it was really interesting to see your data and shown in such detail. Actually, the numbers were quite similar, especially in terms of the carbon isotopes. In South Australia, they go down to, they're between about 0 and -4. So yeah, that kind of might support your observations there. Just my comment was, yeah, following up on Paul's comment about the potential or the hypothetical influence of equilibrium fractionation due to marine ice formation. I'd say that the ones in South Australia perhaps more indicative of potential, if that was the case, of seawater oxygen isotope composition, given that they're exclusively negative in South Australia, unlike the Port Askaig tillite, which may represent formation from seawater. So yeah, I guess more of a comment on that. But then the fact that they are so variable may argue potentially against the fact that they're recording a seawater signal.
Ian, I'd like to just comment for the last minute of the session. Yeah.
Yeah, it's great to hear about that work in South Australia, and I'd hope people would look elsewhere also. I mean, there's been general discussion about concretionary carbonate and assuming that it will have wild carbon isotope compositions, but actually it looks as though it doesn't, and I think that's quite exciting, really. So I guess, is there a stratigraphic trend? I guess that's the question, Max. Do you see a stratigraphic trend in carbon isotopes, or are they just bouncing around all over the place?
Yeah, so I actually looked back at it after looking at your results, and you kind of do see a bit of a trend, although it's not as well defined perhaps as the data that you've seen, towards more negative values. Although you never get down below about -4 for the carbon isotopes. So
I mean, what I'm expecting is that actually this concretionary carbonate is showing more scatter than normal carbonates precipitated within seawater. That there are variable influences of early organic diagenesis that are adding some noise to it. The data from Port Askaig are more scattered at a given horizon. There's about 2 per mil scatter, but nevertheless we still see the trend overall. Given you know, so if you had a complete succession preserved, you know, through the Sturtian time, then maybe you would see an overall trend. It may be that we're just lucky in seeing a lot of the trend here in Port Askaig, whereas you might see only a fraction of it elsewhere.
yeah, I'd say it's similar to what I've seen.
Okay, I'm going to just cut off the session now. You guys can carry on talking if you want to, because I'm leaving the meeting open. I'm going to get a cup of tea, and I'm going to start the next video of the environmental change session at 2:30 our time, 14:30, which is in 14 minutes time. So you've got time for a cup of tea. If Ian and Max want to keep chatting, and Paul, that's absolutely fine.
But I want a cup of tea.